let's do it. And we're going live. All right, welcome back. We are Game 3001 in the winter 2021 semester at George Brown, and it's week 3, part 2 of our broadcast. And the last little video we made was around assignment 2 details. And this what we're doing right now is talking more about steering behaviors, but dynamic steering behaviors, and a little bit of collision avoidance that we're going to be talking about during our lab, where we'll have another video for the lab. Let's talk about that now. So last week we talked about steering behaviors, and we talked about a few of them. We talked about the some kind of seek behavior, some kind of flee behavior. We also discussed what arrival looks like, as well as some kind of wander. We described wander, we didn't do wandering. And in the lab, I showed you a very simple way of moving our object from the source to the destination in a very linear direction. Okay, so that's what it's going to do. Today, we're going to extend that a little bit more and add some more functionality there. So there's many different steering behaviors that we're going to look into, and we're going to get into that right now. One of the things that we see is, we've seen this before with seek and flee. Seek, sometimes also called chase. Again, what we're trying to do is match the position of the target each frame, right? And one thing we're going to do that's different in dynamic steering behavior is it's going to have acceleration, right? Acceleration. So it's not going to just be a linear velocity. It's going to accelerate every frame until it gets to the, kind of our max speed. And then once it gets to the maximum speed, it's going to maintain its velocity, right, as an example, and keep that same velocity for the entire time. Should we have a different scene to show the flee state? No. What I've asked you to do is I've asked you to, if you follow the instructions in the assignment, it tells you basically that you reset the screen and you take all the objects off the screen and put them back again. So please make sure you read the assignment details for that one, so that you, and again, I recommend highly that you guys look at the assignment 1 details before completing it. So this is an example of the flee path. Notice that if this is where I am, here is the target for seek. I can't get to the target directly. Why is that? Because what's going to happen is I'm looking where I'm going. So as I'm looking where I'm going along the path, and then I'm turning around and then finally arriving at my target. And again, when I'm seeking without arrival, I'm going to shoot past it, chances are, keep looping around and come back, and then keep looping around and come back, because I'm going to have an acceleration and so on. When I'm fleeing, it's the opposite of seeking. So I'm going to choose a vector that is direct opposite of my seek location. So instead of going there, I'm going to kind of go into another target away, directly away from this one. And what's going to happen is I'm going to seek to it, but I'm not going to go directly. I'm going to go again in this rounded path. Notice that the path for fleeing is a lot smoother than the path for seeking, where I have to continue to turn. The turning is going to happen around a turn rate, because realistically, my player's avatar, even if it's a character, isn't going to spin on a dime. It's going to have a turn rate where I kind of connect, right? Think about this as a bird or some kind of plane or a spaceship that's flying. It's going to have to turn with some kind of turn rate. Miguel says, so he's going to avoid the seek point. Yes, it's avoiding wherever the point is. It's kind of the opposite of seek, all right? And there's some code in here for examples that have been included here, so you can look at our pseudocode. Again, I'm not going to go through the example code here in class, but they're there. It's there for you to kind of look. What about arrive? And we talked about arrival before. So the seek character always moves towards the target with maximum acceleration, right? Maximum acceleration is the way to say it. And again, a better name for it would be chase, because that's what seeking does. If the character arrives at the target, it will overshoot the target, reverse, oscillate, and orbit the target without getting any closer. That's what seeking does. And I want you guys to show that as a difference between seek and arrive. Arrival is a different thing altogether. Arrival is when things slow down. So again, here is the seek path, right? So it kind of seeks around here. And then what happens is it keeps on oscillating or moving around the target over and over again because it's not going to stop. It doesn't mean when you get to the target, it stops. That's not seeking, right? Seeking is constant. Arrival, what happens is it does something different. It accelerates, and then as it hits some kind of radius around the target, it starts to decelerate until it stops. And it's going to stop exactly at the target area. That's arrival. And you can see that the arrival path is more difficult. If you think about it, you can add arrival after seek. So you have seek, and then what you want to do is you want to extend seek and add an arrival piece to it at the end. So that is arrival. And again, we're just talking about motion at this point, right? So arrive it uses 2 radii instead of 1. Dynamic arrive, in the original one, the kinematic arrive, right? The character gets near enough to the target to stop without trouble. But the new one, right, the second radius is much larger and is used to begin slowing down the character when the radius is passed. And then what happens is the algorithm calculates the ideal speed between the new radius, at which the character speed is maximum, and the target, which the character speed is 0. So what you're going to do here is you're going to do a smooth step, or you're going to do a lerp, a linear interpolation from maximum speed to 0. So you're going to go from 0 to 1, as an example, or from 1 to 0 in this case, where you're going to go from maximum speed all the way to 0. You're going to stop exactly at the point where you have to be. And you can use a lerp for that, okay, which we talked about a little bit last week. All right, so that is arrive. And again, they've got some examples of arrival script here for your viewing pleasure. All right, so this is some stuff. In case, again, you can't figure out the stuff that we've done in lab, I think the arrival script here is pretty good from the book. Okay, align. This is a new behavior. So an align behavior tries to match the orientation of the character with that of the target, ignoring its position and velocity. Okay, so how this works is if I have my target, right, as an example, and I have my original orientation, then what I want to try and do is I want to orient myself towards the target or align with where the target is looking. And one thing to note is to find the direction of rotation, subtract the character orientation from the target, and then convert the result into a range between negative pi and pi radians. All right, so that's the way it's being done for alignment. Okay, so that's align. And they also give example of that here in pseudocode. And then a lot of this this document, even though there's 85 slides here, it's mostly pseudocode. Okay. Again, to arrive, there are 2 vector normalizations, but in the align, we need to normalize a scalar. And it turns out that it's either +1 or -1. So we have a value between -1 and 1. A lot of times we have those ranges. And we talked about this in lab last week. We have a range that goes from 0 to 1, a normalized range. And we have a range that goes to -1 to 1, right? A -1 to 1 is a very common range. Even when it comes to controls, I want to control, my input, and I'm going from -1 to 1, where -1 is to the left and 1 is to the right, as an example. The ship doesn't rotate or align. Correct, Miguel. It doesn't do any of that stuff. It just keeps going right. It kind of slides or slips to the left or the right. Velocity matching. So one thing we do is alignment, and the next thing we do is if an object is in motion, we want to match the velocity with the target's velocity, right? So if the velocity, remember, velocity is a vector and it's pointing in a specific direction. A vector has got both magnitude and direction, and what you're going to be doing is you're going to match your velocity with that of the target, especially when it comes to chasing. In fact, if anything, what you want to do is you want to overtake if you want to, kind of catch the target, right? So an increase, hopefully you can run faster than the target, or you can move faster than the target to catch the target. Otherwise, at the very minimum, you want to match the velocity, so that the magnitude and direction that the target is moving in, and it talks about how to do that in this code. Now, let's talk about steering. So far, what we've been talking about is dynamic movement. And the dynamic movements we've talked about are seeking, fleeing, and arrival. Those are the three types. We've also last week talked about a little bit about pursuit, if I'm not wrong, and a little bit, because I kind of showed you the diagram, and a little bit about evasion, but we're going to talk more about that today. All right. So seek, flee, arrive, and align. They do a lot of the calculations, as an example, that we're going to be using for the rest of, we're going to build on these calculations to create additional behaviors. All right. So let's take a look. So align, you can change your facing, right? And you can, where it says, look where you're going, that script, look where you're going, is very important. And we're going to try and see if we can match this up today in lab. Seek and flee. From that, you can get wander. You can get pursue and evade. You can do path following. You can do collision avoidance, which we're going to be talking about today, as well as obstacle avoidance. Velocity match, you can do arrival, right, as an example, because you want a velocity match if an object is moving and you want to get to that object in flight, right? And there's also something called force field, where we're going to be talking about separation and cohesion. All right, so separation and cohesion. So, and especially when it comes to flocking, we're going to have I'm going to show you a little video, if I can, in lab, where we see some flocking behavior with something called Avoidance. So here's pursue and evade. So we talked about seeking and fleeing. So naturally, what we want to do is, I have a chasing character, and I'm seeking this instead of a static target, the target is moving. So instead of me going directly towards the character or the target where they are, I want to calculate where they're going to be based on their velocity. And the velocity, again, is the direction that they're moving in and the magnitude of how fast they're moving, right? So I want to calculate where they're going to be from where I am. And so instead of me going straight to try and chase the character, I'm going to cut them off at the pass, so to speak, and try and kind of calculate where they're going to be. That's what pursue is. And the opposite of that is evade. They're chasing me. Where do I need to be so that they can't reach me, as an example, as opposed to just fleeing? So we need to make an assumption that the target will continue moving with the same velocity. That is the assumption we're going to do when it comes to pursuit. We're going to assume that they're not going to speed up and they're not going to slow down, right? So we're going to calculate where they're going to be based on the current velocity. And that's the thing that they're going to do. So here is the seek route, where they're going to come up behind the character that's they're chasing. And here is the pursue route, where they're going to do a sharp turn first. They're going to turn first. Instead of trying to go with their thrust or whatever, they're going to make a turn first, and then they're going to go towards where the target is going to be, right? Which is obviously a better way of cutting the target off at the pass, as opposed to following up behind them. That's the pursue example. Okay, and again, there's some code around that, how to do pursue. Okay. And when it comes to evade, if you think about it, it's the same thing. Instead of me kind of going where I'm going to be in an arc, I'm just going to turn to where I'm going to evade the target completely. It's coming after me, and I'm going to turn directly away from it, and turn first and then evade, where I think it's going to be based on its velocity and its current velocity. And I'm assuming that the velocity is going to stay the same. Okay. Face. This is another one. Face behavior makes a character look at its target. Okay. So, and we talked about this. And one thing that comes out of face is something called look where you're going. So look where you're going is kind of an extension of facing the target. So instead of facing the target and just looking at the target while you move, so it's always facing the target, what looking where I'm going is going to do is, imagine that I have thrust, I have velocity, and I'm going to move in a certain direction with a turn rate, like I said. And I can only move or turn based on my turn rate, how fast I can turn to the right. Or think about this as angular velocity. I only have so much angular velocity, and I can only turn based on what my angular velocity is. Okay. And what this looks like is, like we said before, let me bring that up. So again, if I was going to draw out my screen, for a second. Let's suppose I have a line that's useless. Let's suppose that I have my screen. Here's my screen. And let's suppose I have my target, which is kind of way over here. And let's suppose I have my character that's there. And we're going to make it so that it has a facing, kind of what we saw before, which is something that looks like an ugly triangle at the top of my little box. It's not quite right, but whatever. And what I want to do with this is I want to move my object, right? Instead of, I don't want to do this behavior. I don't want to draw a line from here to here and do what we did in class. That's the wrong behavior. Like I said, I want to move forward, right? I want to turn every frame, move forward along my path and keep turning so that I'm moving more or less where I'm looking, right? Until I point to the target and then move closer toward the target. So it's kind of in more of a looping area until I get to the target. When I get to the target, if I'm doing seeking, I'm going to keep accelerating past the target. And then what's going to happen, as soon as I pass the target, I'm going to turn, right? And a lot, depending on where I am, I'm going to, again, move and then turn and then move, maybe even off screen, as I continue to move in the direction that I'm looking, as I'm going to, again, try and circle. And this is a very bad turn rate that I'm showing you, but the idea here is the right idea. This is how your object should be working for assignment number 1, right? As it moves and turns and moves and goes, it kind of follows the look where it's going kind of target. It's going to loop around, it's going to come back, and it's going to keep on making tighter little circles until it gets the target again. Arrival doesn't do this. What Arrival does instead is it kind of goes, there is a, like we mentioned before, a radius. We have a radius. We have a radius around the target, some kind of radius that looks like this. This radius, this outer circle, is where my object is going to start slowing down. So this is the arrival behavior. So let's suppose I made it to here, right? So I'm pointing in this direction now. Let's say somehow I've kind of done this arc to get there. And now what happens is instead of going full force here at the target, you know, as an example, what I'm turning, I'm now starting to decelerate, right? And I'm decelerating until when I get to the target, right, as an example, and I'm oriented properly, I stop. And that is arrival, right? So what's going to happen is I'm going to come from there. And again, if I was going to draw some kind of arc that makes any kind of sense at all, depending on my turn rate, right, I'm going to come and accelerate and let's try that again. You see that I'm not a great drawer as I kind of continue on to the target. As soon as I hit the radius right here, I'm going to start slowing down until I kind of make it right to the target center. So that's kind of what it's going to do. All right. But the radius is something that we want for arrival. Okay. Which is what we talked about in lab last day. Okay. Wander. Wander is very similar. How do we do kinematic wander? We can use kinematic wandering as our seek. And I want you to think about this. Instead of exactly following the target, we can give the target some variation in where it's going, right? So to have a little bit of wandering instead of moving perfectly, you know, at the target. Giving it a little bit of wander makes it a little bit less predictable in terms of you shooting back at the target or the enemy that's coming after you, right? As an example. So that's not a bad idea by allowing wander to happen. Again, wander, what happens is you have this target and you have some kind of circle, you know, near the target that you're going to try and kind of find, you know, kind of land. And think about this as, imagine wandering can also be used as to kind of level your enemy. You know, the higher level the enemy is, then the tighter the circle is going to be around the target. And the lower level, the larger the circle is going to be. So they have some variation in terms of the way they follow you and how smart they are, so to speak. Okay, so that's wander, which is not a bad idea for dynamic moving or motion. Okay. Path following is also a really cool behavior. And one of the really great things about path following or wall following, if you will, is imagine that I have some kind of slope as an example, or it could be a linear path. And what I'm going to do is I'm going to keep a consistent distance from the path while I'm following the target. So in other words, I have a path laid out ahead of time, a curve, if you will, and I'm going to follow the target along a predetermined curve. So the path following behavior basically says I want to keep cohesion, or the distance between the autonomous agent and the path that it's following. Okay, so that's kind of what how path following looks. I'm not asking you to do this for assignment number 1 or even for assignment number 2. Path following has issues. One thing that we can do is if we notice that here is the predicted path as an example that the target is taking. The target, instead of me following in the target's footsteps, because that's what really path following is, I have a target that generates a path behind it. And instead of me following it, I calculate where the target's going to be. And if the target's already past this point, right, instead of me going and wasting my time following its footsteps, I just kind of leap into the next area to kind of hijack the shortest distance that I can possibly turn based on my turn rate and looking where I'm going to meet the target. All right, so that's kind of a bit of a predictive follow. Okay, and they give you some code on how to do that for path following. Path following is pretty cool. It gives you the ability for you to match steps. A lot of times we can also use autonomous agents that follow other autonomous agents. For example, I want, a leader, and the leader is going to have a pack, and the pack is going to follow the leader's path. But at the same time, or the flock is going to keep separated from the leader. So path following is kind of a precursor to more advanced behaviors. Okay, let's continue. There are different path types that we can define. You can certainly define straight lines, so you can follow straight lines, or splines. And depending on which one you follow, obviously it's going to have a different look and feel with line segments over splines. Line segments obviously are much easier for us to create. Splines are more interesting to look at, though. Anything more curved is a nicer on the eyes in terms of its motion as well as the output. One thing to notice is this idea of coherence with path following. Again, one of the challenges that we have with path following, depending on how, for example, what if the target is looping, right? So the target, we're following a path that kind of loops this way. And here's my target right now. And what happening is here is the previous point. Here is the closest point. And now what's going to happen is, I've got a bunch of closest points. These are all, equidistant from the target. I can go here. I can go here. Or I can go here. Which one do I choose, right? And where is the target right now, right? So, depending on which one I choose, I can make the wrong choice. If I chose, as an example, this one, that would be the worst choice for me to follow this path the target's laid out, because I would waste all this time going over here where I can just like skip to this. That would be the second best point. Obviously, the best point would be this one, where I don't have to do any of this. If somehow the target's already done this path and is over here, I want to be able to skip from here as I'm path following over here. Okay. So that is path following in more detail. One thing we also want to talk about when we're in crowd simulations or flocking simulations, we want to be able to maintain separation between agents. So I have multiple autonomous agents or AI objects, and I want them to keep separated. Okay, I don't want them to somehow crash into each other or conjoin in some way, right? So in order for us to do that, we have the separation algorithm. And the separation algorithm says, hey, you know what? I want a minimum distance to the left, to the right, behind me, and in front of me. And what I'm going to do is I'm going to create almost like a space cushion around my object, right? I'm going to adjust my velocity and my direction based on the object that is next to me, or the object that is in front of me, or the object that is to the left of me or behind me, to create that separation effect. It can be quite complex, and usually what we use for separation is knowledge of other objects in the scene, right? And so what we want to do is we want to have a maximum acceleration, and what we want to do is we want to be able to make sure that there's a minimum distance, calculate the minimum distance between where we are and other objects in the scene, and so that the effect, and I can't show you collision avoidance, but basically, or sorry, separation is like, let's suppose, go back to my drawing, instead of having only one of these, and let me just undo this this drawing here. Let's suppose I have more than one of these, right? And I want to both of them want to make it to this. Well, what's going to happen is, let's just copy this one. So I'm just going to copy this one. So I want to keep a separation, and I want to calculate the minimum distance between these two objects as I go towards this, kind of towards the target. In the beginning, it's not a problem, but as I come closer, you're going to see that they're going to converge in paths. So for example, again, if I just try and do a carefully laid path, let's suppose that I can turn at this rate, and the target is moving, so it's a bit of a curve. I do the same thing for the other path, so I have a little bit of a better path. It's not going to do this, right? It's actually going to do this, where I'm going to kind of go straight, and then there's going to be a point where it's going to converge onto the other path like this. Well, this point here is where I want to keep separation. So as these objects move in synchrony towards my object, instead of doing this, I want the objects to kind of move apart, right? And keep that distance, as an example, which is going to modify their velocity and direction, right? So they're going to keep this minimum distance between this and this, minimum separation. And this is for every other object in the scene, right? So separation is definitely a steering behavior. It's a little bit more complex because you need to know about other objects in the scene and their direction, okay? So that is separation. One thing I've asked you guys to do in assignment number 1 is something called collision avoidance. And this is something that is an advanced behavior. We're going to be working with this a little bit in class today, and I'll be talking about some strategies around collision avoidance. In fact, I want to spend a little bit more time talking about it here in lecture to give you guys kind of some insights on how to do collision avoidance. How do we do collision avoidance? And what is collision avoidance? Okay, well, let's get back to this. Let's suppose that I have an object, right? And this is my target. So let's move the object in place. Right, so again, I'm just going to grab this, and we'll move it here and turn it into the direction where the object is. So let's suppose I start here now for the object, and I want to go from here to the object. So let's just draw a line segment that goes from the start to the destination object. So this is where we want to go, right? Well, what if there is an obstacle like so in the middle of my positions? And let's just for to make this a little easier to look at, I'm just going to move all this around. So I'm just going to move all these 3 things just down a little bit to give myself a little bit more room. Okay, so there's my start, and here's my end, and there's an obstacle. How do I avoid it? Does anyone have a sense of how this is done? How do I do that? And by the way, if I'm directly aligned in the middle, which way do I turn? So I have some people coming on the mic. Anyone have some suggestions? Again, I have Eric. You've come on the mic. I can mute you if you want, if that wasn't intentional. And Yang Hui, and there's Sinan.
Yeah, it might people go in or random up or down.
You could do random up or down. That's also something we could do, almost like we use RNG, random number generation, to generate one thing. But how do you know when to start turning, right? That's the thing. You're going to collide with this thing. If I go maximum acceleration, and George, I'll come to you in a second. If I go maximum acceleration, again, from one place to the other, 1 second, George, and let me just show you this. So I maximum accelerate this way. When do I turn? Do I turn there? No, I got to be able to turn earlier. Okay, George, you have your hand up. Go ahead, talk to me. What other things can we do, George?
If you attach collision to the vision, so like their line of sight.
We could make a line of sight, yeah. Neil says you need to have a circle collider around the ship. We could do that, right? A little bit of a radius. Problem with that is which way to turn and how to continue to turn towards my direction. So this is a bit of a problem. And let me go into the PowerPoints for a second to show you this. So let's suppose I want to avoid another stationary character. Well, notice that I have these little feeler lines, if you will. I have 2, and I have 2 from here, right? And what we want to do is we want to have, a way of avoiding the collision as we come closer. And this is important. Collision avoidance is important for separation, right? If we want to maintain separation, we don't want to collide with each other, right? We want to avoid this collision. Here's where we're going to collide. And I can tell that both of us are going in the same direction, right? But we don't know. Each one of these things is autonomous and has its own brain. And so it doesn't know that it's for sure going to, collide with this thing unless it starts pre-calculating its neighbors, things that it can detect of where it's going to be, right? So there's a couple of things we can do. One is to have something called feeler lines, right? These little feelers. So I can have a feeler here and a feeler on the ship like this. Okay, so when it's moving, I have these little feelers. And what people have done in the past is they've created these little circles around the feelers, all right? Like whiskers, exactly. And these whiskers, there's 2 or more. And let me explain why these whiskers are in play. And let's put another one. Let's put a third one in the middle. All right. So again, these whiskers are, let's say, the same length approximately. And you can see that here I have, here I have the some kind of radius like this. Why do I put little circles here? Because it helps, right? This is one way of doing it. And there's nothing wrong. There's different methodologies that we can use to create this thing. So example would be, that was odd. Let me just try that again. Sorry. I didn't quite copy everything and left a little mark, and it bothers me. Let's go there. And yeah. And so again, let's suppose that I'm in the middle. I collide with the first circle, which is here. I know I need to turn in some direction. Let's say I start turning. So I start turning now, right? And I go forward a little bit. I can't turn immediately because I have a turn rate and I have a speed. I have an acceleration. So I kind of move into this part. Notice that now two of the lines, this one and this one, right? They're colliding, right? I just decided to turn right. So I keep turning, right? And moving, turning and moving. As long as these lines are colliding, I keep turning and moving, right? But then what happens is I might get to the situation where, if I don't turn and move enough to avoid, I might get to something that looks like very close to the turn rate that I'm going in. So now I keep turning and I'm not clear yet. And now I'm clear. And so what's going to happen is I want to seek to the target at this point, right? So I'm going to turn back. So I'm going to start turning back. So I'm going to move down a little bit and then turn back towards the target. So I'm turning towards the target now. Move down a little bit, turn back towards the target, and keep doing that, right? As I'm avoiding, the target, I'm still going to do another seek algorithm, right? As I'm coming towards the target, it's going to change my path, right? Based on the obstacle, depending on my turn rate and so on. And you're going to see that depending on the turn rate, that this is going to be something that I'm going to be able to do. Maybe I'll meet the target at some point. And you get what I'm saying here. And again, these feelers can also be used for things like arrival. So I can see that, okay, I've hit the outer edge of the arrival radius, and I'm going to start arriving and slowing down, right? So this is definitely a way of doing it. The other one that Neil recommended, what about if I put in some kind of outer radius to this thing? So that's another way to do it. So let's say, for example, I have an outer radius. It's not what I wanted. Let's say I have an outer radius, I said. So I'm going to draw an outer radius here. And let's make it so that the outer radius maybe is something that's reasonable, where I can start decelerating, something like that. Well, there's an advantage of a radius and like this, so that it kind of goes outside of the my bounding area. So my bounding area is basically saying this is when a collision will occur if I have a bounding area. So when I collide from this shape to this shape, okay? I want to collide. And usually my bounding area is some kind of, let's say, a square that looks like this. That's maybe my bounding area, all right? That kind of, encapsulates the object inside, whatever the ship looks like on the inside. I want to encapsulate it with some kind of box collide. But this other sphere up here, and again, I'm just going to do some erasing so that I can undo this change here, just so that way I can avoid capturing these lines here for a second. Let's just make sure that you can see what I'm doing here. And again, I'm just being a little bit more careful. Yeah, let's get rid of some of these lines for a sec, just to make sure I have this like multi-headed hydra here, okay? And let's just go back to this, and I want to capture this whole thing here. And now I'm moving, and I can still have the little feelers, but let's avoid the feelers for a second. Let's suppose I'm disregarding the feelers. So I'm coming towards it. I hit the radius with my object. I turn, and then now I can do two things. I can keep turning to avoid the path altogether, right? Which is a little bit less realistic, all right? So I can do that. Or I can move closer to some degree, keep turning, move closer, keep turning, slow down, right? So I can avoid contact with the object as much as possible, right? Keep slowing down, and you can see I can come really close, and then kind of go down to this point here where I can turn again, right? And again, I'm just exaggerating here, but I can turn, let's say at some point, and I can keep making it so that I can avoid the object. So again, there's nothing wrong with some kind of outer circle and the series of circles where you can say, here's my outer circle where I'm going to start slowing down. So that's another option. So I have this inner circle where I'm going to actually turn. If I hit this circle, I've got to do a sharp, kind of turning or whatever, right? But I have an outer. I can make it so that I can decelerate if you want to make it more realistic, right? So again, let's go back to the pencil, and let's also go to the circle. And let's suppose that I have an outer circle. Ooh, that's an ugly pencil too. Let's go to that pencil. And let's go to an outer circle that's way out here where I start decelerating. So I start decelerating at this circle, and then in this circle I'm turning when I hit this circle. By the time I hit this circle, I start turning. From between here and here, I'm going to decelerate, slow down so I can avoid hitting, move, and then when I'm clear, I accelerate again to another point. So it's definitely some way we can do it. Okay? So this is definitely a way of doing it. The other way of doing it, let me just push all this back to the way it was before. Let's suppose I have my feeler lines again, and this is the way we're talking about it. But every object has some kind of destination nodes. So we know that every object has is this collision area. Maybe what we can create is a series of nodes. These are invisible, by the way. Okay, let's suppose we have a series of nodes. Here's a series of nodes. Okay, just making these up. Okay, so let's suppose these are the nodes that I have, right? Well, instead of seeking directly to this, I don't have line of sight, let's suppose, immediately. I don't have line of sight to this thing, all right? So I know that I can detect, instead of having these large lines, as I move my character closer, all right, and hear me out, this is another strategy that you can also use, right? As I'm moving my character closer, I hit the first line, right? The first kind of like outer node, right? And now I decide which way to turn, whether I'm going to turn this way towards this node, or whether I'm going to turn this way towards that node. Either way now, I'm not I have a middle target, if you will, a temporary target where I'm going to try to avoid. So I hit this one, I move forward a little bit because I'm going to move along my path. I start to slow down and I turn towards this node. All right, so again, I move forward a little bit, I keep slowing down, and I'm arriving at this node, right? So move forward, turn around, right? And, you know, I'm kind of going down this way, make it a little quicker, and maybe I turn a little bit faster. And then I arrive at this node right here, this node. So I know there's kind of a middle step between where I'm going and the actual object, right? And now what I'm going to do is in preparation to get to the next step, I'm going to follow, sorry, I just want to make sure that it's back to where it's supposed to be, which is here. I'm going to follow my path to get to the place where I want to be, which is my target. Sorry about that. But so it's going to look something like this. When I get to this point here, I'm going to start going in the right direction. So instead of me calculating which way to turn or whatever, or where to go, I'm going to create these little path nodes around my obstacle. And I can think of, if I had every obstacle in my scene, if it has little path nodes, these things can help me navigate around the obstacle as well. Okay, so to help, little helper nodes, if you will. All right, again, more computationally expensive than trying to figure it out on its own, but it's going to be a little bit smoother, and it's definitely a trick to make sure that it looks a lot nicer. The other thing to do, and one thing to do, is when we're calculating line of sight, and one thing we talked about is this idea of line of sight. How do I calculate line of sight in the first place? What is line of sight? And we're going to talk about line of sight as we get into sensing radius in the second half of semester. How do I calculate, you know, kind of line of sight, you know, with my object? How do I know that I have line of sight here? What's the way to do that? If you think about it, just by not mathematics or with an algorithm, but just help me out here. I want to calculate, though, I have line of sight, yes or no? What are your thoughts? Do I have line of sight here, yes or no? No. Why? Because I can't draw a line between this and the obstacle, right? From where I am right now, okay? Okay, how about this? Does this node have line of sight? So if I draw a line from here to here, you know, let's draw a straight line, not a crooked line. Does this node have, does this node have line of sight from here to here? Right, it would, right? And how about this node? This node also has line of sight from here to here. So does this node, right? So does this node. Okay, so does this node? It kind of does, let's suppose. These nodes have line of sight, but not this one, right? So what I can also keep track of, which of these nodes has line of sight, and instead of seeking to a node that doesn't, so I'm going straight, and my feeler line connects with a node that has no line of sight. I'm going to go towards the nearest node by keeping track of which one that is from a distance perspective with my craft. I'm going to turn towards the nearest node with line of sight towards my target. And then when I turn there, I'm going to, as soon as I arrive there, I'm going to move towards that node again, but also keeping cohesion or a minimum distance from my obstacle. All right, so lots of different ways to handle obstacle avoidance, but this is the most complex part of assignment number 1 that I've asked you guys to do. It's going to be the one point of consternation for a lot of you, how to make it happen. Sean says make a giant sensing cone or square. You could do that. There's lots of ways to accomplish the same thing, but here are the basics. So with dynamic movement, you want to have both acceleration and velocity. Okay, we don't want to just have velocity. We want acceleration as well. So that's the first thing. So with a dynamic movement, we need acceleration and velocity. All right. And for this rigid body, when you approach an object that you need to avoid collision with, you want to decelerate. If I can spell decelerate properly, that was right. Decelerate. You want to be able to decelerate, and you want to decelerate when you hit this object, when you come closer to the object somehow, right? And what you want to do is you also want to use arrival, right? So we've been making you use arrival as a thing, but maybe what I want to do is I want to arrive, kind of at this place right here, and then I want to reorient my path, as an example, which is my my target, my seeking, right? Until I get to this part. So basically, what I'm doing is I start by seeking. So I start by seeking. So seek behavior or chase behavior. And again, this is for an object that is stationary, that is static. Okay, we're not talking about a moving object. Although the rules be the same for a moving object, it would just work slightly differently. So let's suppose I start seeking. I get to a point where I need to turn, so I start decelerating. I turn until I arrive at my my avoidance point, and then I start seeking again. So then I start to do the seek, right? So I start seek again. I start seeking again, right? And so again, it's almost like I'm combining behaviors. And this is where we have this advanced behavior kind of makeup, right? I'm combining behaviors where I'm now seeking towards the target until I get to there and I arrive, right? So there's arrival again, right? So arrival. Okay. And I wanted to draw this up for you so you kind of get a sense of that this motion, when it comes to obstacle avoidance, and this is a great example, high level of obstacle avoidance or collision avoidance, as an example. Obstacle avoidance or collision avoidance, this idea, there's many ways to handle this. Seek some kind of whiskers, some kind of sensing radius, some kind of avoidance path that's around every obstacle, or searching for nodes in the grid that have line of sight. Okay. One way to do line of sight is line collision detection. So again, you can think about two lines when they cross. You have a line segment and another line segment. If there's a collision between the two lines, or if one line has points that are contained in another line, you have a collision, right? And the collision, it's going to be somewhere, like I said, like around at this point, right? So this collision point, as an example, if there's a collision before any kind of collision before the target, so I have kind of a source object. Here's my source, and I have a target object, right? And let's suppose this is my target. If there's some kind of collision between the source and the target, source and destination, then I don't have line of sight. Pretty simple, right? If there's no collision between, if I draw a line, an imaginary line, a line of sight, right? And there's no collision between my source and my target, then I have line of sight. What's more complicated than this is where my line of sight, it's not really true that that's the way sight works. Sight actually looks more like a cone, like was mentioned by some of us. Let's say, for example, I have a cone of line of sight that looks kind of like this, right? So anything that's inside of this cone is the things that I can see, right? As an example. And if I can't see close to this this cone, to this object that's behind this one, what happens is I can think about drawing like path tracing or path whatchamacallit, if you will, ray casting. So imagine if I ray cast, I have this kind of array that casts here, here, and here, and I'm ray casting to my object, right? I'm casting several rays, and you can see that I don't have a ray that connects with my object. If I don't have a ray that connects with my object, no line of sight. But I have several rays that are coming out at the same time. Maybe I even at a much wider line of sight. Maybe even something that looks more like this, where I can see a lot more in front of me. So Neil asks, is ray casting multiple lines? It could be just a single line, right? But if I want to create shadows and I want to create almost like this sensing radius or line of sight, I can definitely use rays to cast, from my object. Now, ray casting is expensive because I'm casting multiple lines, typically like this, in front of me. And then what happens is these lines would collide with obstacles. And if the lines collide with obstacles, I have collisions with obstacles, but I don't have any one of my lines, any one of my rays connecting with my target, then I don't have a line of sight. This is more accurate, but much more difficult to pull off, as an example. And so a lot of times what we do is we simplify, right? And we say something like, I have a radius, an arc that I can see in front of me. Something like, as an example, maybe something like 90 degrees, right? As an example, or maybe 60 degrees, 60 to 90 degrees is what I have in here, right? So I have, again, some kind of arc of sight, if you will. And anything in my arc of sight is where I draw some lines, and I draw multiple lines. Let's say, for example, I might have 4, that kind of come out from here. And, or more, 4 or more lines, let's say many, many ones. And the more I have, it's more accurate line of sight detection, right? The other way to do this, instead of using a number of, it says, so maybe we could initialize the number of games that it checks, or limit the frames. Yes, my autocorrect, sorry. It could check how many frames, or how many times it's checking every frame, for sure. But then what's happening is you might miss a check, you might miss an alignment check. So this is definitely one option for line of sight. The other way that we can do line of sight, and I'm talking about it earlier, and I'll talk about it again later on this semester, is instead of doing it like this, then you make a shape, all right, an actual shape, which might be the easiest thing to do, right? And let's suppose the shape is something like a box, right? So I have, let's suppose, a shape that's floating in front of me that looks like this. Okay, I can probably see all the way down here, and it's kind of literally moving in front of me, and to the left and to the right. Maybe I'm a little bit short-sighted on my flanks, right? But the shape can look something like this, right? If this is my shape, and I can say, okay, am I overlapping with my target? The answer is yes. Okay, am I overlapping with another target that's inside? How many of objects, let's say, for example, I have another, some kind of other shape here, and there's another shape here, as an example. Is there another shape that I'm overlapping with that's closer than my target? And the answer is yes. I have two of them. I have one here, right? So this is some way you can do it. I have one here, and I have another one here. These are the two shapes that are closer from a distance perspective, from here to here. Those two shapes are closer than this one. This is farther away. These two shapes are closer. Okay. From those shapes, as an example, where is the direction that I'm looking? I'm looking in this direction. So I have a line, right, as an example. So I have this big shape here, but I also have a line that points directly from my character, my autonomous character, to my target, right? Is my line colliding with any shape that's closer in this area, this collision area, than my target? Okay. So here's my target. Instead of casting many rays, is what I'm saying, right? Here's my target, and this is my source, my start, right? Here's my start. Okay, and I want to seek the target. Are there any shapes that I'm colliding with this big shape, as an example, that is closer to the target, that I'm also colliding with a single ray that casts from my the nose of my ship? Why is that? Because if I only made a single ray like this, right, again, that's really not accurate line of sight. Not really, right? There's also line of sight over here. There's also line of sight over here. There's line of sight everywhere. But I can calculate that I don't have line of sight because there's multiple contacts as well as my target. So that is the answer, yes, yes. And can I draw a line between me and the target without one of those contacts that I detected? Multiple contacts, 1, 2, 3, 4 shapes in my contact range, right? There's a contact that's closer to me that I have collision with my central ray, right? that is much closer to me than the target. Right? And then I can determine if I have line of sight or not. All right. So again, lots of ways to handle the same concept. Obviously, ray casting is the most accurate of them, and we use ray casting for graphics as well. If I want to calculate shadows, as an example, perfect shadows on an object, I can cast multiple rays. And let's just do that again. Let me just undo those changes. Let's suppose instead of this is my start and this is my end, this is a light as an example, and I'm casting rays, which are basically just straight lines, from this multiple places. And what happens is, notice that if I cast rays, then I'm going to produce an umbra, right? An area that has shadow, right? In this area here, right? This is the area that's dark. This is the, shadow, right? Because I'm projecting an area that has, and there's other rays here. Let's suppose there's rays that go in all directions, okay? But here, for this light, if this is if it's just a point lamp, as an example, I'm casting light everywhere, but not in this area because it's occluded by this shape right here. And here we're in shadow, or here in my object is inside the umbra of the light, right? And this is another way of thinking about line of sight, where I cast multiple rays in an arc in front of me, like I said, and if my shape is not caught by one or more of those rays, no line of sight. That's the most accurate way of doing it. Okay. So why am I talking about this? Because we're talking about collision avoidance. And collision avoidance and obstacle avoidance are two different things. Collision avoidance means when two objects are moving dynamically, and I know that as I approach, I'm probably going to collide with another object. I calculate the other object's trajectory and mine, and I say, you know what? I want some kind of separation between the two objects. Okay, that's collision avoidance. Obstacle avoidance is where I'm casting, like it says, a single ray or more. Usually I cast more than just a single ray, right? And when I cast a single ray or a whisker, right, what happens is I try and figure out if I'm going to collide with an obstacle before I get to my target, okay? And that's what it's kind of doing. So here it shows a triple ray cast, which is very common, which is what I showed you the first time. And what I want to do is, if I have a single ray cast, the problem with this is I'm probably still going to hit because this ray is not hitting. And so my object can only sense what it can see with a single ray. Whereas if I have multiple rays, I can this triple ray cast is probably the easiest way I can sense where I'm going. And so I can avoid, or I can turn away from this object towards my my target and start turning a lot earlier, start slowing down a lot earlier than what I can do with this ray. I wouldn't slow down at all. In fact, I would hit in this case, right? And there's a bunch of different kinds of tactics we can use for ray casting. One of them is a central ray with short whiskers. Okay, that's one option. Another one is parallel side rays, where I have two side rays that come out in a certain distance. Another one is just whiskers, and the third one is a single only. And there's also variations on any one of these things. Okay, this is just some different configurations that you can use for obstacle avoidance. And later on, we're going to see that this is also the way that we're going to be able to do line of sight. Okay, so line of sight. Again, the challenges are with corners. Corners are weird, right? I can see that I only have two rays as an example, and I see that both of them are colliding, or one of them is not. I want to turn towards the ray that is not colliding, right, as an example. And then what's going to happen is I'm still going to hit because of the corner, right? So instead, what we can do is, this is another option, is using some kind of collision volume, which is what I talked about before. So instead of using a single ray, I've used some kind of capsule or a box, which is a lot more accurate in some ways than just a couple of rays. The problem with using a box is that you'd have to use object aligned bounding box, an OBB, which is more complicated than an ABB type collision, right? Axis aligned bounding box. This would not be axis aligned. This would be a collision volume with a corner, and that would be way more complex than several rays, as an example, to cast. Okay, most likely. But yeah, but this would be very accurate, much more accurate in some ways. How many rays are you going to cast before you know that you're not colliding with a corner, right? Or that it's a corner that you're colliding with. So there's tactics that we've talked about so far in terms of collision avoidance. All right. I also wanted to talk about really briefly. There is some great stuff online about flocking with voids. Okay, so if you want to look at some great images online, and I'm trying to look at this is on YouTube. I want to see if there's a GIF, an animated GIF. Here it is. So here's an example of flocking behavior, as an example with voids. And what's happening is they have interesting behaviors where they combine, they do different kind of following, and then they separate, which is kind of interesting. So, it looks like flocking of birds, and all they're doing is they're following simple algorithms, right? As an example. So here's a flock of birds, and what we want to do is we want to make them flock in the same direction, or doing leader following, if you will, which is kind of interesting. Here is, let's see if I can find something that's an animated GIF, right? So we don't have to use YouTube. Here's where, again, you have cohesion, separation. They're trying to separate from each other, kind of come back, and they almost look like fish as they kind of, or birds as they move around. And this behavior is something that you can create, okay? And there's some great resources online where they talk about things like separation, alignment, and cohesion. And these three behaviors are the things that you can add to a void, V-O-I-D, in order for you to have this kind of behavior. I encourage you to look for some, if you're interested in this kind of behavior, if you're someone who likes artificial intelligence and you wanted to make flocking and things like other kinds of tactics, you can do that by taking a look at voids and flocking. And it's not just by looking at images like this, but actually there is a lot of resource online. Even if you look at voids on Wikipedia, they've got some images that come from the main kind of articles that are out there about voids and flocking and steering behaviors. That's where they come from. And if you look, you can find a ton of resources online where they actually show you the algorithm for alignment, for cohesion, for separation, and for moving in and out of following a leader, as an example. So very, very interesting behavior. A lot of times what you can also do is you can use this steering behavior with with flocking for things like missiles or particle systems work great like this too. So I want some kind of flocking behavior or for particle systems to kind of one thing to follow and one particle to follow another particle in a certain path, and it can make really cool, interesting effects like portals and like explosions and like smoke and a bunch of other stuff by using these simple steering behaviors in different combinations. So kind of really cool. So take a look at some of these things. I think this is the original one by Craig Reynolds back in 1987 or 1986. Let me just copy this and I'm going to put it as content inside of our Blackboard so you can see it. So this is flocking article. I highly recommend you take a look. I think it's some really great information, kind of thing on here about those kinds of steering behaviors and how that works. So take a look at it. I think it talks a lot about it. There's a lot of little videos. This one is from QuickTime that you can download. You can see how old it is if it's QuickTime, right? I wonder if mine would work. Mine's probably not going to work. But these are, yeah, there's SIGGRAPH articles that you can certainly download from and so on. So kind of really cool from flocking behavior. And it talks about everything from, there's other resources that you can look like in terms of how to create artificial life-like motions for flocks and herds and schools of fish and a bunch of other stuff from SIGGRAPH, which is, kind of a conference that is kind of held every year for things like different kinds of behavior. If you actually look up SIGGRAPH.org, there are a ton of papers here that you can look up. Everything from graphics to different kinds of AI, machine learning, and a bunch of other stuff. And they got some great videos here that you can watch on SIGGRAPH, right? So really cool stuff. And I'm really only scratching the surface of all the things that you can see in here. And there's obviously one that's going to happen, SIGGRAPH 2021. This is coming later on this year. I think it's probably going to be remote, and there's nothing wrong with learning how to sign up for this kind of stuff. But they talk about everything from arts and gaming and interactive kind of technologies and techniques that we can use for things like VR and for things like machine learning and artificial intelligence. All right. Questions around what we talked about today. So today we talked about some dynamic steering behaviors. Last week we talked about kinematic steering behaviors, which are you go to the maximum speed, there's no acceleration, there's no smoothing. Here there's acceleration, here there's smoothing. And we also talked about several other types of techniques with path following, jumping from one path to the other, as well as the idea of collision avoidance where two dynamic objects are moving, and finally of obstacle avoidance with a static object. And you're guys going to be doing this one, some kind of obstacle avoidance that you're going to be using. All right, any questions around any of this stuff that we talked about today? All right, so in lab, just a reminder again, if we look at a couple of things on Blackboard, okay, and let's take a look at our assignments. So assignment number 1 is due this Sunday, January the 31st at midnight, guys, okay? January 1st, it's an individual assignment that you've had. It's worth 10% of your final grade. Again, please don't wait to upload your the details of what's due for assignment 1 at 11:50. Okay, I would recommend that you start submitting about an hour earlier. Make your target 11 o'clock in your mind, worst case, or earlier than that. If you can submit between now and Sunday, don't wait till the last minute to submit. Get it done, get it out of the way, and move on to other work. You've had a couple of weeks to get this done. Work on it. And what this does for you, the reason why it's individual is it gets you primed on coding. It talks about how to use the framework that we've given you, and it'll make you a more productive member of your own team in game production too. So please don't just wait to get this done last minute, or try and talk to other people and say, hey, so what did you do? How did you get this done? Try and work it out on your own with the things that I've given you. And then if you're stuck, talk to others and see what they've done compared to what you've done, right? To get some ideas. We're going to learn some things about look where you're going today, and we're going to talk about avoidance a little bit in lab today, a little bit, but the avoidance is really for you to do with the algorithms that I've given you. One thing that we're going to also do is kind of draw that line. When we turn, I want to be able to draw that line that's in front of me from the kind of the direction my ship is looking, depending on where I'm looking, and we can kind of work out how to draw that line that's in front of us, almost like a debug line that's being drawn from the start, from the front of our ship, in kind of front into the direction we're looking. Okay, that's what I'm going to do today. And then once we have that debug line, then we can kind of calculate if there is a line collision detection, and that's the way we can create our whiskers. And I'll show you the collision detection algorithms that we have that I've already supplied for you in the assignment framework. Okay. All right. Any other questions before I let you guys go for today? And for the people that I'm seeing in the first lab, again, it's happening at 12. For the second group, again, we're meeting later on today. And I believe that's at, is it 3? Last week it was a little early when I did stuff, and we started early. It's 4 o'clock. So the first one goes from 12 to 2, and the second lab is from 4 to 6. So let's make sure we meet at 4 o'clock for the last part of our lab, and kind of go over. That's the one I'm going to record for today and put it up on YouTube. And I may make 1 or more recordings, so we have a couple hours there. Okay, any questions at all before I let you guys go? Okay, guys, lots of information that I've shared with you. Please don't wait to the last minute to start looking at this stuff. You're going to need some of these things for your assignment number 1. And again, we're going to meet and work that stuff out together during our lab periods, now at 12 o'clock and then at 4. All right, guys. Otherwise, for the people who are in the lab, the lecture is completed. I'll see you guys during the lab. Thanks so much.